We appreciate you all joined this invited talks. We have Nate Stemen here, who is a quantum software developer at Unitary Fund. And today we are going to hear some fascinating topic. Um, Welcome, Nate, and shall we start?
Yeah, sure. Great. So, yeah, thanks for having me. Happy to be here. I'm going to talk a little bit about open source software. I'll talk a little bit about quantum computing, and then I'll talk kind of about some of the work that I do at Unitary Fund and kind of trying to grow this ecosystem that is starting to form and that we're hoping to encourage around this intersection of these two topics and that are kind of very important ones, I would say. At least, one is very historically important and the other is hopefully future important. And yeah, so I'm totally open to questions during the time that we're here. We don't have to save them to the end. So if you want to interrupt and ask something, please feel free to do so. I'm going to try to keep it somewhat surface level. I'll talk a little bit about some of the technical things about quantum computing, but if you have questions about the technical aspects of stuff, feel free to shoot. Also, my email is on here if you have any questions for afterwards. If you want to shoot me an email or just get in touch afterwards, feel free. So without further ado, why don't we just jump into it? So the first question really to ask is open source software? And in short, I mean, this can be summarized as, any sort of computer program or application whose source code is available to the public, allowing anyone to view, modify, and distribute it. And over on the left here is some, like, in my mind, some of the most popular open source projects, some of which maybe, if you're not a computer person, you may not know that they're open source. And so what this really just means is that, like I just said, the code is online, freely available to people who want to download it and modify it. And, maybe you have some bug in Firefox and you want to take a crack at it. That's exactly kind of what the point of open source software is. So basically every software, I don't want to say every software, but a lot of the software that you use on a day-to-day basis, chances are there's probably someone working on an open source alternative, or if it's not open source itself. So I like to use Firefox, but Chrome is really the most popular browser, which part of it is actually open source. So that's another one that could go on here. And the open source software and kind of free software community have been around for a while now, and basically since the start of the internet and a lot of these other things. And there's kind of some core values that come along with the open source software movement. I'd say three of those values are transparency, collaboration, and then licensing. Transparency, since all of the development of these projects is done with the code being out there, it's kind of inherently transparent. And obviously you can kind of imagine some of the benefits that come with transparency, just in terms of auditability and in terms of people being able to get involved in these projects that, if it's closed source, obviously you have to get a job at a specific company if you want to work on, something that's closed source, and that's a huge barrier to entry. So open source software really is lowering the barrier to entry to, a lot of these technologies, and it's a lot of how people get involved in whatever their niche is in software. The other big value in open source software is collaboration. So, for something like Firefox or for something like Android, it's a huge project, and there's thousands, probably hundreds of thousands of lines of code that go into these projects, and that's not maintainable by one person. And so there's lots of people who need to be involved, and lots of people who are doing similar jobs, maybe doing the same job in terms of writing code, but then there's also people who are have directing the project in terms of what features do we want to build, what do we want to avoid, and just helping steer the project. So there's lots of different people who are involved, and yeah, like I said, for some of these bigger projects, it's really an effort in collaboration and bringing minds together and creating things collectively. And then one of the last things which I guess is important to mention about open source software, and I don't know if it's a value in and of itself, but licensing is a huge topic. So when you write a piece of code, and let's say you write some program and you put it online, if you don't attach a license to it, it's technically in the public domain, but you haven't necessarily given people permission to go and download it and use it and modify it. And so licenses are a way to tell people what it is that you are okay with people doing to your software. And there's tons of different licenses that are out there. You can see over here in the pie chart, kind of a breakdown of what is common. And then here in the middle, you can kind of see what restrictions and also what licenses allow you to do certain things. And so, there's lots of different people who are on like the very strong, like, I am okay with people doing anything with my code. And then people can also require, for example, for example, the Apache BSD and MIT licenses, you can use the software for a closed source project. So example, if you want to make a product using an open source project, you can do that. But with the GPL and LGPL licenses, you can't really use this open source code to build a product on top of it, unless that product is then itself open source. So there's restrictions that you can place on the code that you write. And I think one of the underlying values built into the open source software community is that the more development, the more code, the more software that is out in the open, the stronger tools, the better tools, and a better ecosystem that we can build because of that very fact. And that's kind of the same the same idea that we kind of embody at Unitary Fund. And I'll get into more about that in a bit, but the idea being that, if we have a solid bedrock of tools that we can all use, then we'll all be better because of it. I think the saying goes, a rising tide raises all boats, and that's very much a theme in open source software. The more open source software we have, the more cool things we can build. Okay, so that's software. This talk is titled Quantum Computing Meets Open Source Software, and I want to give some introduction about what is quantum computation, maybe a little bit about why you should care about it, or what who should care about it rather. So in order to frame what is quantum computation, I think it's best to understand a little bit of the physics behind quantum. And so quantum computation is really the use of the physical theory of quantum mechanics in doing computation. And quantum mechanics is the physical theory of things that are very, very small. And we could put this on a spectrum of, like quantum mechanics governs the physics of things that happen on very small physical distances. And as you scale things up, as things get larger, quantum mechanics no longer has as much of effect, and you go into other physical theories. So for example, when you're talking about planetary motion, you're talking about galaxies, you're talking about hugely massive objects, you're talking about a different physical theory, and that's the theory of general relativity. And we're not going to talk about that at all today. Just to get ourselves thinking about, okay, so quantum computation is using the laws that were discovered in the early 1900s about how very small things interact to somehow aid in the manipulation of information to do computation that the computers that we're all talking to each other on today cannot do, or cannot do in a reasonable time frame. So if we take a step back, I kind of want to give a little bit of historical context to what is quantum computation. So playing a little bit fast and loose with the history of science here, when we started understanding, the physics of thermodynamics, we were able to then harness that information and build, things like steam engines and well, I think mostly steam engines. I'm sure there's some other stuff, but that's mostly what I know. And this really gave birth to, a lot of new type of technology being able to be driven from this new understanding of physics that we had. And there was a lot of, circular motion here in terms of, we learn something about the physics, we can then apply that in the technology. Maybe you learn something in the technology that then informs your physics, and there's this really nice cyclical flow of information and knowledge that happens here. And so anyway, the idea here is that, understanding this new area of physics was able to progress us as a civilization into like a new era. And then again, as we understood the physical theories of electrodynamics, maybe 200 years later or so, we had Maxwell write down his famous 4 equations on how electricity and magnetism work and the dynamics of those. We were then able to harness that knowledge of physics to build, something like computer. And, obviously we could do some, electronics without the full theory of electrodynamics. But really, again, we have this like cyclical flow of knowledge in terms of, we understand some physical theory, and then maybe we're able to apply that understanding to build technology that harnesses that understanding. And so that kind of gave rise and use to, things like computers and other calculating machines. And so now we've had an understanding of at least some of the basics of quantum mechanics for over 100 years now. And like I said, quantum mechanics is the physical theory of things that are very small. So here is the example that I put up here is the, describing hydrogen, how the electrons, are moving or are existing around the nucleus. And so we have, so basically quantum computation is like the pinnacle of things that we could do using knowledge of quantum mechanics. There's lots of other quantum technologies that have come of our understanding of quantum mechanics. For example, a laser is inherently a quantum mechanical process, and so a quantum computer is one of the quantum technologies that will hopefully come of our understanding of quantum mechanics. But like I said, there's lots of other technologies, quantum sensing, quantum metrology, like a lot of other things that could be born of, or that are being born of our understanding of this physical theory. And like I said, a quantum computer is like the kind of the pinnacle, the high, well, at least currently the highest form that we can think to use this the theory of quantum mechanics in terms of getting it to do stuff for us. And the idea is, it's very similar to that of a normal, what a lot of us in the field would call a classical computer, which is, to do computation, to do, whether that's run numerical simulations, whether that's to, a lot of things boil down to numerical simulations, but solving some partial differential equations or doing some forecasting for weather or financial markets, right? Create a machine that can do all those things, but with a very different infrastructure or very different architecture than that of a classical computer. So to go a little bit into the physics here, we're not going to go too deep, but but if you're interested, feel free to ask. In quantum mechanics, we have to throw away a lot of our intuition about how the world works in order to understand it. And it's famously a hard subject to understand because of this. It just because of the way it breaks a lot of our intuition. And so there's two core properties that quantum mechanical systems have that are potentially the reasons that quantum computers can do computations in faster ways than we can do on a classical computer. And the first of those two properties is called superposition. So, if I have a basketball in my house, just to mimic the example that's on the screen, you could say the basketball is in my house. But if I put it outside my house, then it's outside the house. But if I have some sort of electron in my house, you don't always know exactly the electron is in my house, right? It could have in the physics lingo tunneled to go outside of my house, and somehow it's in some what we would call superposition state. And so really this is somewhat of an artifact of the way the mathematics works in quantum mechanics, but basically the idea that a quantum system is in a definite state doesn't really exist until you do what's called a measurement, or really when you look at it, basically. And this will often come across in the pop science literature, that quantum systems can be in many states at once. And this isn't necessarily a horrible way to understand it, but it's not literally true, right? Like in the example, the electron is not both inside and outside my house. Rather, it's in a state where we cannot say exactly where it is, right? There's some probability distribution that governs where it is, but it's it's not like our intuition wants us to say. It's not exactly here. That is until you do a measurement, at which point you can find out where it is. But in doing that measurement, you may disturb it in some other ways, and it may go flying off after that. The other physical property that goes into quantum systems that is unique to quantum computing is that of entanglement. And this is the idea that two quantum systems can be correlated in a way that they can't necessarily be classically. So just to go through the example that's on screen here, let's say we have two photons and they are entangled. So we could be in one of two states. Let's say if they're entangled in this particular way, if I look at the first photon and I see that it's red, then I automatically know that the second photon is blue without even looking at it. The other option for this particular entangled state is that if I measure the first photon and I see that it's blue, then I would know that the second photon is red, again, not even without looking at it. And you may say, okay, well, isn't this a property that classical bits could have? If I have two bits, meaning a bit just being a 0 or 1, couldn't I program it so that if I look at the first one, then the second one is the opposite of that? And that's true. You can simulate that effect using classical bits, but it's not the same inherent process, and it's not exactly it's not quite the same thing. So these are the two properties that quantum systems have that classical systems do not have. And I guess before going further, there's a point to be made here about what we know about the theoretical computational power of a quantum computer versus that of a classical computer. And we know that there are problems that are very hard to solve on a classical computer. And for example, one of those hard problems is that of factoring large integers. And in the early 90s, a mathematician by the name of Peter Shor published an algorithm that factored large integers in a way that was much faster on a quantum computer. Now, in the 90s, there aren't any quantum computers, rather. So this is a purely, theoretical algorithm, but it's still kind of one of the things that we look to in the field of quantum computing as, when will we be able to do, such an experiment where we could factor a large enough number to, break some sort of encryption scheme that relies on the difficulty of this problem. And so that's one particular example of of us knowing that a quantum computer will be faster than a classical computer. I say we know that it will be faster. Theoretically, I don't think there's been a single problem that has been theoretically proved that quantum computers can outperform classical computers. It's a lot of, we've tried for a really long time to come up with classical algorithms to do something, and someone found a quantum algorithm to do that thing faster. And so that's kind of just like evidence that quantum computers have more capability to do, in a sense, more computation in a given amount of time. And again, I'm not going to go into how the algorithms actually work, but they're relying on these two properties here, that of superposition and entanglement, to manipulate information, to use like the popular science terminology, to like try out different potentialities at the same time. Like I said, that's not exactly the most accurate way to think about it, but I also think it's not a horrible way to consider it on first glance as well. So that's kind of the background of quantum computation. Again, staying at a very high level. I guess maybe now is a good moment to stop and just see if there's any questions about anything that we've talked about so far, and see if there's any. Okay, if not, we can move along. So, okay, maybe we have a little bit of historical framing. We understand roughly what the idea of quantum computation is and where it's getting some of its power from. And so the next question is like, a lot of companies are spending money and time and a lot of money really to get a potential thing working. So like what really is expected to do? And so I have this quote up here, and this is a quote from Richard Feynman, who is one of the the leading theoretical physicists of the 1900s, and he was actually one of the first people to propose that quantum computers be a thing, really. And he said, nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy. And besides from being just like an awesome, fun quote, it's really true. If you want to do a simulation of some sort of quantum mechanical system, I showed earlier on one of these slides. So this is the Schrodinger equation, and it's a partial differential equation. And for real systems, it's a nonlinear partial differential equation. And even if you don't know what those words mean, the thing that you should take away is that's really hard to solve for complicated problems on a computer. I mean, it's doable, when the systems get too big, it's not always doable because our computers are just not big enough to handle the amount of numbers that basically need to be thrown around in order to simulate large quantum systems. But if you have a quantum computer, you have something that's inherently quantum, and so simulating quantum systems is much, much easier. And so some of the applications of doing quantum simulation, one of the biggest ones is that of drug discovery. So when researchers want to make a new drug, they have to go through a huge process of trying to figure out, before they even do human testing or animal testing, really any sort of live animal testing, you need to have some basis of understanding of how that drug is going to interact in the body. And that's a big chemistry problem that's oftentimes very hard to know exactly. If I have some chemical compound and I want to say, what happens if I put this in a human body, there's lots of potential interactions that it could have. And for each one of those interactions, you need to understand, okay, what's the byproduct? What's going to happen if this actually happens inside a human body? And doing all of those simulations is very, very, very computationally expensive. So if we could speed up some of those computations on a quantum computer, we could imagine that there are huge savings to be had, and potentially these pharmaceutical companies, while I don't think they necessarily have the best track record for doing things that are best for humanity, they could potentially find more helpful drugs more quickly, with a tool such as a quantum computer. The other interesting application of quantum simulation that I know of, and one that I think is really interesting, is that of understanding what's called the Haber process. So I don't have a picture on here, but the Haber process is the chemical process by which we, and by when I say we, I mean like us as a human civilization, make fertilizer. And obviously everyone needs to eat. Growing food is a hugely important and resource intensive process, and fertilizer is a big part of that. It's something like 2% of the entire world's energy power goes to making fertilizer and using this thing called the Haber process. And the chemical interaction in the Haber process is not very well understood. I mean, it is in a sense, because it's everyone uses it, but squeezing efficiency out of it is not something that's easy to figure out how to do. And so if you have a quantum computer that can simulate the Haber process on a large scale, you might be able to find ways to say, oh, if I increase the pressure during this step, or maybe I add a little bit more of this substance at this step, then I can get the Haber process down. I can increase the efficiency of the Haber process. And given we're spending 2% of the entire world's energy output every year on creating fertilizer, if we can cut that down by 25%, that's huge, right? So this is an example of, I think, a really small win that would have a huge impact. And obviously, we're not, no one is guaranteeing that such a thing can be found, but that's just two examples really of things that could have, in my mind, a pretty great benefit for that of humanity. Over on the right here, I have forecasting. There's a lot of different types of forecasting: financial forecasting, weather forecasting, that are really complicated processes, and again, involve most of the time very complicated nonlinear partial differential equations. And again, this kind of problem is well mapped onto a quantum computer, and there is potential for doing better forecasting. So there's definitely quite a few banks who are interested in already starting thinking about how a potential quantum computer could affect their business. And it's interesting too, because even though at the moment we have quantum computers, like this picture on the right is a quantum computer. I don't know exactly which one it is. I can tell you it's a superconducting qubit device. It's potentially the one that Google has, but it's very small. And when I say small, I mean it's small in its computational capabilities. This actual machine that you're looking at here is probably as tall as a person. I'd say it's probably 5-6 feet tall. So it's very big. And that whole device has to go into what's called a dilution refrigerator. And the term refrigerator here is used very, like, it's true, it's a refrigerator, but it really cools everything down to, instead of, close to 30 degrees, this is cooling things down to like almost 0 Kelvin. And the reason that this is because quantum systems are very hard to control. Like I mentioned earlier, the moment I look at a quantum system, it's very easy for it to just fall apart, or what we say in physics is decohere. And so the best way to help avoid some of those, major problems is to cool your quantum systems down to, as cold as you possibly can, because there's really two things. We're going to cool them down as much as we can, and we're also going to pump out all of the air, the gas, every extraneous potential interaction that our quantum system could have. We're going to remove it. You could imagine if you have some quantum system and you have some gas that's also there, the quantum system is so small. If a gas particle comes over and touches it, or interacts with it rather, it's gonna have some effect on the quantum system. It's like if you're doing a classical computation and every once in a while some of your bits just get randomly flipped, that's going to drastically affect your computation. And the same thing happens with quantum computers, except not just can you have a bit flip, like a 0 going to a 1 and a 1 going to a 0, you can have way more complicated types of errors happening on the quantum computer. We could go from one superposition state to another, but again, another superposition state. So there's lots of crazy complicated science going on that's understanding the noise of these quantum machines. And that's actually part of what I work on. So happy to talk more about that. But to get back to it, we were talking about some of the potential applications of quantum computing. So we talked about forecasting, and then earlier I mentioned how in the early 90s there was an algorithm published by a mathematician who found a quantum algorithm to factor large numbers. And so if you're familiar with cryptography at all, you probably know that one of the main things that is good in cryptography is hard problems, right? That's kind of the foundation of creating a new cryptographic scheme, right? You find some sort of hard problem, then you find a way to use the hardness of that problem to make sure that when you send a message, for example, you would have to solve that very hard problem in order to actually read the message, unless you know some specific information. And so factoring large numbers is exactly the type of problem that has been used as a basis for secure cryptography over the past, I don't know, 30, 40, 50 years. I don't exactly know the timeline, but it's in very common use. So if you ever hear RSA encryption, you're hearing about an encryption scheme that is using the difficulty of factoring large numbers in order to provide that security. So if one had a large enough quantum computer, you could, in theory, intercept, someone's internet traffic and decrypt it and see, monitor what someone is doing. And there is serious concern now that, governments are potentially already doing this. Bad actors are already doing this. And but you may say, well, Nate, why does it matter? You know, if someone intercepts my traffic now, we don't nearly have a big enough quantum computer to actually decrypt, or decrypt these this information. Well, you know, you can store the information for a long time and, you know, decrypt in 15 years, for example, when we have a large enough quantum computer to do such a thing. You know, hopefully, you know, no one is really going to be snooping on our internet traffic, because, you know, who cares in 15 years what we're looking at now. But you know, potentially, if you're a government worker and you have access to privy information, then that's a different story. So the US government has already started rolling out new encryption schemes for what is called post-quantum cryptography, and that are encryption schemes that are resistant to quantum computers. So the National Institute for Standards and Technology is kind of one of the big people organizing behind this. And yeah, there's lots of interesting work to be done there. People are still proposing new stuff, even though there've already been schemes proposed that are proven to be, or that are very well understood to be resistant to quantum computers. So if we didn't do anything to change our encryption schemes, then yes, as quantum computers become larger and are capable of doing this kind of thing, then yeah, internet security and, you know, any sort of encryption would just, you know, basically be useless. But thankfully, when someone comes up with a smart idea that can be used for bad, smart people also think about, you know, okay, how do we avoid this situation? And we're in, I think, pretty good hands in that way. So those are some of the reasons I think that you should care about quantum computation, that is. And so I guess the next question for technologically inclined people is, you know, what is a quantum program, and, you know, what does it look like, really? You know, there's lots of mysticism, I guess I would say, about quantum in general. And so I want to try to demystify a little bit about, you know, what this actually looks like. So we talked a little bit about like the things that we operate on in classical computing. You know, the computers that we're talking on today, where the transistors are, you know, doing computations on bits, right? So you have some sort of 0 state and 1 state, and on the classical computer, that's created by having some sort of, like I said, transistor that has either voltage flowing through it or voltage not flowing through it. There's no in between. There's no voltage is, you know, going, you know, slowly through it. No, right? It's either it's on or it's not. In quantum computation, we have the 0 and 1 state for the things that we operate on, but there's this whole mix of other things that could be valid superpositions of those states, and you can kind of think about it as a sphere of possibilities. And then in terms of the operations that we can actually do on them, we represent this graphically using these kind of like electrical circuit-like diagrams. And so each one of these boxes is, you know, some sort of operation that we're performing on the qubit. So the X operation that you see on the second qubit, the first operation that we're doing, that's the standard, you know, NOT gate. You know, so basically, say in classical world, if you have a 0, it goes to 1, and if you have a 1, it goes to 0. The H gate is, you know, something that we can't do on the classical computer because it puts the qubit into a superposition state. And you know, there's some other things here, but we don't really need to go into that. And then in terms of you know, how would you actually write something like this? This code here does not correspond exactly to the diagram, but the idea here is that, you know, you would define some sort of qubit, and then you define the operations that are going to happen on that qubit. And then in this example on the bottom, we're going to do an X gate, like I said, the NOT gate, but we're going to do the square root of it, right? So it's raised to the 0.5 power. So that's the square root of the X gate. And again, that's not something that you can do on the classical computer. right? A NOT gate on a classical computer says 0 to 1 and 1 to 0. And if I do the operation twice, you get back to where you started, right? You do an X gate on a 0, you get to 1, you do an X gate on a 1, you get back to 0. But we're saying there's an operation in quantum computing where you can do, basically half of a NOT gate. So it just, it kind of boggles your mind every time you think about what are the possibilities that you can do on qubits instead of bits. And the one thing I want us to take away from this slide is, we're really pretty early on in the developmental arc of quantum computing, right? If you've written software before, you know that 99% of the time, unless you're doing something like extremely low level, you're not working with bits, right? You're not saying, oh, and now flip these bits and then flip these bits, right? You're saying, get me this list, compute this, this function on the list, and then store this in some sort of data structure. Yet you're working at like a relatively high level of abstraction a lot of the time. With quantum programming, we're still pretty much like at a very low level, right? We're working with qubits. We're working with the actual physical operations that you can do on those qubits. So, there's a lot of experimentation that needs to be done in terms of quantum programming language. This one here that we're looking at is a project from Google, which I'll show a little bit more on the next slide. But it's an example of open source software coming into quantum computing. And yeah, again, the key takeaway is here that like, we're still, you can think quantum computing is very cool because we can look back on the history of classical computing and say, oh, we're there at our development. And we're very much like at the point of, we have huge vacuum tubes and the computers take up entire rooms, and you need expert operators in order to like help operate them. And they don't do very much useful. Actually, quantum computers don't really do anything useful at the moment because there's still like more science experiments than they are, technology. But we're getting there. We're making lots of progress, and we're getting bigger and bigger machines. Okay, so we talked about open source, we talked about quantum, and now, first of all, why and how are these things coming together? So these are just some of the many examples of projects that are open source and have some communities built around them in terms of people developing them. And like you can see, a lot of the ones I've highlighted are quantum programming frameworks. So just like the one that we saw on this slide. So this is actually written in Python. It's a package that you can just download and then start writing your own quantum programs. And a lot of these are as well. There are some other more program specific or really programming languages developed around quantum. But there's really a wide variety of tools that are being created, and there needs to be a wide variety because there's lots of like interesting problems to solve. I see that Morgan, you have your hand up. Do you want to go ahead and ask a question?
Nate, as I'm listening to this, I'm wondering what the connection will be with the quantum movement and AI in an open source environment.
Yeah, I mean, so I can tell you that quantum and AI, like people are thinking about quantum machine learning. I can tell you that. Definitely initially when it first started becoming a thing, thought, oh, okay, people took these two huge buzzwords and are just mashing them together and are seeing what's coming of it. I think that there are some genuine improvements that quantum computing can offer artificial intelligence and machine learning in terms of speeding up some of the training of these huge models, using less physical resources and energy. In terms of the open source software, I can tell you that there are frameworks for doing kind of like machine learning oriented quantum computation. So it's definitely like there are tools. As to how it'll affect the entire ecosystem, I don't think it's going to have like a huge role, I guess. I guess I'm thinking about, how machine learning and AI has like a pretty big effect on, for example, the Python ecosystem at the moment. And there's just like so much money being poured into AI that inevitably it's going to have its effect on Python, which has become the de facto language for a lot of these artificial intelligence machine learning things, at least for the beginnings of them. And so I guess, yeah, maybe it would it'll start having more of an effect on it once we get bigger and big enough machines to do such computations. But like I said, our existing quantum computers are pretty limited at the moment, so it's that effect I think will maybe be seen a little bit more down the line.
Thank you.
Yeah, of course. Thank you for the question. Okay, so yeah, this is just a small snapshot of really some of the open source tooling that's kind of coming out now. And again, we're thinking about this from like a rising tide raises all boats kind of thing, right? The more tools that are out there, the more experiments that people are doing in this realm, the better future tools that we can build, right? And so that's really part of the mission at Unitary Fund, which is where I work. So Unitary Fund is actually a nonprofit, and our mission is really to create a quantum technology ecosystem that benefits the most people. And we recognize that technology as an industry and as a sort of organization has it's had its faults along the way, and so we want to try to make sure that we can steer clear of some of those faults with quantum computation moving forward. And so we have two kind of pillars that we rely on at Unitary Fund. One, we run a micro grant program, and two, we do some of our own research. So starting with our research, we have two main projects. We have the Mitiq project, which is mostly what I work on, and it's a toolkit to help you run your quantum computer with less errors when you're running it on a quantum computer. And then we have another project called Mitiq. You'll notice that basically all of the any open source quantum project that you come across is probably going to have a Q smashed into its name somehow, and we're no stranger to that. And Mitiq is a community benchmarking platform. So if you go to mitiq.info, you can find some more information about it. But really, it's to try and help the ecosystem track its way to creating a useful quantum computer, one that's really powerful and can do all the things that we just talked about. Yeah, I see Papaya has their hand up.
Hey, hi. Can you hear me?
Hi. Yep.
So the toolkits that you're referring is more, you guys understand the user scenario, because in a quantum computing, there is a lot of other scenarios where each organization may be working. So it's more, you look at the less possible error. How do you quantify the scenarios? Because I may be looking at breaking an encryption cert, right? Or someone else may be looking at like, hey, what is the next weather patterns looks like? So possible scenarios are different in each case. But I'm just trying to see how the toolkit that what you described is like, hey, does you look into the possible scenarios and then failures, or is it more in coding?
So are you asking in particular to either of these projects, or are you just saying in general?
In general, like how does your toolkit that you're referring plug into those models and help them run faster, or at least run in less error manner? Yeah.
So for the Mitiq project, which is what you're referring to, it's really an active field of research as to how to actually go about doing that. So I can't give like a quick answer really. I'm happy to share some more info after this, but yeah, as for how we actually go about taking a quantum program and running it on a real quantum device with less errors, you know, there's all sorts of techniques that people have proposed and that people are researching to try to see, you know, what actually is the best way to do exactly that. And it's not a solved problem. There's lots of ideas floating around. And so the idea with our project is to make it public, to make it very available to people to kind of run these error mitigation, how do you say, error mitigation techniques, and, you know, to try them out on their workflow. There may be some that work really well for, you know, financial applications and doing that kind of thing. And then there may be some techniques that, you know, don't work well with that and they need a different technique. And so part of our goal with Mitiq is to, you know, implement many different techniques. And so people can, you know, try out different things and see what works best for them. And really the idea, yeah. Great, thank you for the question. And the idea with our research is, you know, academics have some incentive to create, you know, certain tools. Companies have an incentive to create other tools, you know, that are maybe turning into a product. And that leaves some gap in the middle. You know, academics are really good at writing research papers, creating new ideas. Industry is really good at productizing things. And there's lots of in the middle ground that need to still be created in order to create a really beneficial ecosystem for anyone who wants to use a quantum computer. And that's part of the things that we are developing, is that we think that those are kind of like slotted in the middle there somewhere. The other big thing that we do at Unitary Fund is we run a micro grant program. So for anyone interested in writing open source quantum software, we've already given out almost 90 micro grants, and this is $4,000 with no strings attached. So we don't get any ownership. We're not some sort of venture capital fund, but we're just there to provide mentorship and provide resources, provide, you know, answer questions, connect people where we can, and really help the open source ecosystem grow in a more sustainable way. The classical computing ecosystem, open source ecosystem, you know, has been struggling for a long time with how to actually pay people and, you know, get people rewarded for all the volunteer work that they do. And there's lots of interesting ideas that are coming out of that space. And so, you know, this is kind of an experiment with one of those ideas. And like it says here, this is really aimed at people who are exploring in quantum. So whether it's writing a new quantum programming language, whether that's, you know, a grad student who wants to publish their library and make it more legitimate, whether that's, you know, just a hobbyist who's playing around with stuff, you know, it's really just whoever, you know, people apply, and we take a look at the applications, and, you know, there's a lot that goes into this that we want to, you know, help make a flourishing quantum ecosystem. And with that, I have some resources, you know, for people who are interested in learning more about quantum computing. If you're interested in any of the work that I talked about, you can join our Discord. It's discord.unitary.fund, and it'll take you to an invite link. And yeah, happy to keep in touch with people here and answer any questions that we have here. So I see, yeah, Papaya, you have another question?
Yeah, just curious, like, I know you guys develop the software and then interact, but like, do you guys have a lab, like, or you have an access to the lab? I know it is a big infrastructure unit, $millions of dollars funding. So you guys work on hands-on, or it's more of like you do simulations, or like what kind of exposure?
Yeah, that's a really great question. So the company that I work for is actually fully remote. So I purely dabble in the software realm, really. Thankfully, well, yes, we can do simulations. So whenever we want to study a new error mitigation technique, we can simulate how it performs on small quantum systems. And then thankfully, there are some quantum computers that have been put online. So for example, IBM has put some of their devices so that, if you want to send a quantum program to their device, they can run it for you and give you back the results. So that's an opportunity to run on real quantum devices and see the difference between what happens when you do a simulation versus what happens when you run on state-of-the-art machines that are, like I said, they're small and they're not always great. There's still a lot of noise that affects these computations, but we're really slowly improving all of the metrics that we're going to need to make a really big, fast, functional quantum computer.
Yeah, thank you.
This almost sounds like the batch operations that they used to run in the 1970s before the internet.
Yeah, I'm not sure I'm super familiar with that, but if it's the idea of like sending stuff away and getting the results later, it's exactly like that.
Yes, that's exactly what it was. But the difference was it was being done on IBM 360s as opposed to quad. Okay.
Yeah.
I put a link in the chat about the Unitary Fund.
Oh, thank you.
And I think we're running up close to 5:30. What I was going to ask everybody to do is to turn their cameras on after you finish sharing your screen so we can all say hello. And Ashi, if you want to take a picture of the whole group, I think that would be putting a face to everybody who's here. Come on, everybody's got cameras. This isn't like dealing with high school students where they tell you their camera isn't working, so I tell them to pull out their phone because I've all got them. Come on, there's some more. Come on, we got to get everybody here.
Smile.
Everybody. Okay, and then also please share this information. Keep going. Keep going, Jeff. I know that, if people are paying attention, they're going to be on here. Zandra, hopefully I'll be talking to you tomorrow. Maram, you haven't been feeling well. We'll give you a pass. Okay. Ashi, is that a good enough? Can you get a screenshot of everybody?
Yeah, let me do it again.
Hold on. I'm going to do a print screen too. See if that helps. Okay. Please, everybody, thank Nate for his presentation. I mean, this is really, truly cutting edge stuff that we're dealing with today.
Thank you, Ned.
Yeah, of course. Thank you again for having me. I really appreciate everyone's time. If I actually can't send a message in the chat, but my email is nate@unitary.fund. If anyone wants to send me an email, feel free to follow up. And yeah, happy to share any resources or anything if you're interested.
Okay, so it's NATE@Unitary Fund.
.fund. Unitary.fund.
Fund. Yeah, I was kind of wondering how it's a nonprofit. I was wondering where your funding comes from.
Yeah, that's another great question. So since we do our own research, we're on some government issued science grants. We were also recently awarded a grant through the National Science Foundation to do further open source ecosystem development. So those are two pretty big sources of income. We also get donations from a lot of the big companies that are involved in quantum computing. They see a lot of benefit from the work that we do in terms of creating all of these tools and helping foster people who are interested in developing talent and doing some of the workforce development. So yeah, it's really those two main things: doing our own research, getting grants for that, and then donations.
So Nate, I had one other quick question for you. Is this your full-time gig, or do you work on this? You have a regular job and then this is your This is what you do when you're not punching a clock.
No, so this is my full-time job.
This is your
Yeah,
full-time.
this is how I punch the clock.
This is your passion, and you get to live what you love, or love what you
Yeah,
live.
it's pretty cool.
That's really neat. And you're a Seattleite as well, aren't you?
Yeah, I live in Seattle. I live in the like Central District.
Cool. Okay, so everybody, you've got his email if you don't take use of it, and we might have some aspiring open source programmers here.
Yeah, and if it's just general questions about software, you know, feel free to shoot me an email. I'm totally open.
Okay. Ashi, is there anything you want to do to wrap this up?
No, just to thank you all, and Nate as well. Thank you so much, and goodbye.
Thank you, Nate.
Great.
Thank you,
Thank you,
everybody.
Nate.
Thank you.
Yeah,
Have a
thanks,
great
Nate.
day.
Thank you.
Thank you.
Thank you.